Hi everybody. I'd love to introduce Hahn from University of Arizona, and he's been working on statistical analysis of cosmological data with SimBIG. Welcome, Changhoon.
Thank you. Thanks so much for having me. Yeah, so today I wanted to tell you about one of the projects that I've been working on, which is trying to analyze spectroscopic galaxy surveys with a framework that I've developed called SimBIG. So let me start with a brief introduction, since I imagine this is a very broad audience. So at the moment today, we've established a sort of a standard model of cosmology that we call Lambda-CDM. And according to this model, the universe starts with a Big Bang. There's a period of rapid exponential growth called inflation that seeds the initial perturbations in the primordial plasma of the universe. Then after recombination, when the photons decouple from the plasma to what we observe as the cosmic microwave background, the baryonic and dark matter in the universe, they gravitationally form all of the structure that we see today, like the stars, the galaxies, and the large cosmic filaments and all of these structures. Then around 10 billion years from the Big Bang, the universe enters a period of accelerated expansion that's driven by dark energy. So in addition to providing this nice complete history of the universe so far, one of the primary reasons why cosmologists favor the Lambda-CDM model is that it's been remarkably successful at describing current observations. So I'm showing you here what is the temperature power spectrum. I'll explain more whether power spectrum is later, of the cosmic microwave background, or CMB. And in blue points are measurements from Planck, the Planck satellite. And in Lambda-CDM is a prediction of our cosmological model. And you can see that we're able to reproduce in great detail all of the points that we measure in the data. The other really remarkable feature of the Lambda-CDM model is that we describe all of these observations with just 5 parameters. So I've listed these parameters here. There's the first parameter is omega matter, which tells you how much matter, including dark matter, there is in the universe. There's omega baryon, which is how much baryons there are in the universe. H or H naught, depending on how you parameterize it, describes how fast the universe is expanding. Then there's the NS parameter, which describes how the ripples in the early universe were distributed in the primordial plasma. And then sigma 8 sort of quantifies how clumpy the universe is on large scale. So despite the fact that our model is able to describe the observations very well, none of the main ingredients of Lambda-CDM are particularly well understood, whether it's inflation, dark matter, or dark energy. And we're in a particularly interesting time in cosmology because this standard model has come under a lot of scrutiny because of cosmological tensions between measurements that probe the early universe versus measurements that probe the late universe. So let me explain what these tensions are. So I'm showing you here measurements of the growth of structure parameterized using this S8 parameter. And I'm labeled in the top right here measurements from experiments that probe the early universe with the cosmic microwave background. So compared to these measurements, experiments that probe the late universe with weak lensing find significantly lower values of S8. Now, in addition to this S8 tension, we also have another tension called the Hubble tension. So I'm showing you here measurements of the present day expansion rate of the universe, parameterized using this H naught parameter. And again, I'm showing you measurements that probe the early universe with CMB in blue. And in comparison to those measurements, what we find in measurements that probe the late universe with supernovae are significantly higher values of H naught. So as the precision of our experiments have improved over time, so has the statistical significance of these tensions. So one way we can inform both of these tensions is using spectroscopic galaxy surveys, like the one I'm showing you in the background here. So this is the Sloan Digital Sky Survey. And what surveys like SDSS provide are photometry of all of the galaxies that it observes, as well as detailed spectroscopy of the galaxies. So the spectroscopy and the photometry can be used to measure the angular positions of the galaxies in the sky as well as the redshift, which is the velocity of the galaxy. So then you can use this information then to make nice maps of galaxies, three-dimensional maps of galaxies in the universe, like the one I'm showing you here. This is from the SDSS survey. And the distributions like these, they encode a tremendous amount of cosmological information. So for instance, we can probe the growth of structure through these features called redshift space distortions. So I mentioned that one of the measurements from these galaxy surveys is redshift, which is the velocity of a galaxy. And there's two components of this redshift. First comes from the cosmological expansion of the universe. And then the second component comes from the peculiar velocity of the galaxy. So the velocity, the particular velocities of the galaxy within the expansion. So if we only had the first term, this is what the galaxy distribution would look like in what we call real space. But because we have these peculiar velocities, this distribution becomes distorted in redshift space like this. And there's two regimes of this distortion. First is these long elongated structures that we refer to as fingers of God. This comes from the virialized motions of galaxies within virialized structures. So things like galaxy clusters or groups like that, which if you look at it in velocity space, then become elongated. Then there's a more subtle effect, which I'll flip back and forth to. And if you focus on some of the overdense regions here, you might notice it. You'll see this squashing along the line of sight. And this is due to what's called the Kaiser effect. And this comes from the fact that there is a coherent motion of galaxies towards the large structures in the universe. So you can use this effect then to probe how much structure there is and what the growth of structure is over time. So to make it a little more quantified, a little more concretely, I'm writing here the overdensity of galaxies in redshift space, and this is all in Fourier space. So K represents that, and you can write this in terms of the overdensity of galaxies in real space, plus this additional term that depends on the growth rate of structure and the matter overdensity. So in practice, what we do is we measure something called the galaxy power spectrum. So, and then extract the information about the growth of structure from there. So the power spectrum is measuring the excess probability of finding galaxy pairs at certain separations over a random distribution. So here's what the actual galaxy power spectrum looks like. These are measurements from the Sloan Digital Sky Survey at two different redshifts. Again, this is in Fourier space. So small values of K represent large scales, and large values of K represent small scales. So we can measure these power spectra at different redshifts and then measure the growth history of the universe from the 3D distribution of galaxies. The other information that we can also extract from the galaxy distribution is the expansion history. So I'm showing you a video here that is giving you the history of, like, showing you the evolution of the universe from the primordial plasma when baryons and photons are coupled together and they propagate as spherical sound waves. Then after recombination, the photons decouple from this plasma, and then the baryon acoustic oscillations are frozen in place. So as the video here is illustrating, what that means is that today there's an excess probability of finding galaxies at this separation. So if we were to look at the probability distribution, excess probabilities of galaxy pairs at different separations, we'll actually find this excess probability at the length scale of the baryon acoustic oscillation, or BAO. So we can use this as a standard ruler to then infer how much the universe has expanded at different periods of time throughout cosmic history. So despite all this information that's in the galaxy distribution, the way we currently extract this information is by first summarizing the 3D distribution into two-point clustering statistics that I've already mentioned, like the galaxy power spectrum. And we model this clustering statistic using perturbation theory, which is a linearized solution to general relativity and the fluid equations, assuming that the fluctuations of the overdensities are relatively small. So this assumption breaks down as you go down to smaller and smaller scales because the fluctuations of clustering become increasingly large. So we are currently limited to analyzing large linear scales below this black dashed line that I've marked. But of course, there's more information beyond the scale, and there's also more information beyond just summarizing the statistics into two-point clustering. So here's an example that I really like to show, showing you two distributions that by eye are obviously very, very different from each other. But if you were to measure their power spectrum in blue and red, you'd find that they're basically identical. But if you look at any of the higher order statistics, like the bispectrum, which measures the excess probability of finding galaxy triplets of different shapes and sizes over random, you'd immediately be able to tell that they're different distributions. So the question is, how much cosmological information is actually available beyond the current analyses in the galaxy distribution? And so to answer that question, collaborators and I built these two suite of cosmological simulations called Quixote and Molino. And so what these simulations are M-body simulations which trace the evolution of dark matter from very early times in the universe when it was homogeneous all the way down to present time. So a little bit slow video. But you can see here how the gravitationally all of this structure is forming in these simulations. And then afterwards, once you have the dark matter distribution of the universe, we identify these compact structures called dark matter halos, and then afterwards, we populate them with galaxies using a halo occupation framework, which statistically populates halos with central and satellite galaxies. And these models have been very effective in describing how galaxies cluster. So what these simulation suites provide is all of the ingredients to do what we call a Fisher matrix forecast. So this is the equation for the Fisher matrix. There's two components to it. One is you need enough simulations to estimate the covariance matrix of whatever clustering statistic you're interested in. And you also need simulations to estimate the derivative of the clustering statistic with respect to different cosmological parameters. So I've listed here the 5 Lambda-CDM parameters, and we have a number of other additional parameters that describe how galaxies form within halos. So with these simulations and with the Fisher matrix forecast, we can make these sort of predictions about how precise the measurements of the Lambda-CDM parameters will be if we were to analyze, let's say, the power spectrum alone versus the power spectrum and bispectrum combined in orange. So the contours here represent the precision level. So smaller contours mean more precise measurements, while larger contours mean less precise. So immediately from this forecast, you can see that with the bispectrum, we can constrain the Lambda-CDM parameters much, much tighter than with the power spectrum alone. And we also show, I won't go into details about this figure, but there's also a lot of additional information on nonlinear scales. So I've marked here you can see the current limits of analyses, but there's a lot more information as you go down to smaller and smaller scales. And at this point, I've had a series of works that looked at this for different clustering statistics. And really the consensus that these works were able to establish is that there's substantially more information in the galaxy power spectrum, in the galaxy distribution than in the power spectrum alone. So now the question is, how can we actually extract this information in the galaxy distribution? So if we were to try to extend how we currently do this with using the analytic models based on perturbation theory, well, one of the challenges we face is one I already mentioned, which is that our models are inaccurate on small scales. So this is a figure showing you the bispectrum as a function of scale, k, and the blue error bars are showing the theoretical uncertainties. So you can see that as you go down to smaller and smaller scales, and if you go beyond the current limits of 0.2, you're completely dominated by the theoretical uncertainty. So there's no way you can extract that information. Also, there's no analytic models that are currently available for analyzing many of the statistics that the community has demonstrated is better than the galaxy power spectrum alone. Another main challenge is
Let
that
me understand actually this part. So
yeah.
now the galaxy's power spectrum is kind of the distribution of sizes of galaxies, and you're doing local spatial structure and different measures of local spatial structure, correct?
So the galaxy power spectrum is also a measure of local spatial structure, but it's only 2-point statistics. So you're just looking at galaxy pairs and how, so you just count up how many pairs are this separation apart compared to what a random distribution is. But now we want to look at additional higher order information, like galaxy triplets or galaxy quadruplets and all of these combinations.
Okay, got it. And then, for the finer granularity, is it that you don't have enough observations, or that the model becomes so flexible that you need a lot more data than before to resolve it?
Well, so then what happens is that at the moment we don't have the models to actually predict what these measurements should look like if we stick to the analytic models. So there's no way to compare the two and then measure what the cosmological parameters are, the Lambda-CDM parameters.
So is it the family of you don't have enough pixels to work with, or is it that you have to worry about internal galaxy, like gas ejection events and all the nasty stuff that requires galaxies to be internally modeled?
So at the moment, it's not really the modeling challenge that's the problem. It's that right now, the models that we use are analytic. So they're based on...
These are differential equations that are, I'm sorry, they're just pure differential equations. They're not like simulations that are encoded like in finite form. Okay.
Yeah. So I'll go into a little more detail. I think it'll be a little bit clear when I explain how we can solve some of these problems. So these are the challenges with the analytic modeling. There's also the challenge, which is that observations are very messy. So I've shown you that video and a couple of other images where it was nice, pristine distribution of galaxies. But this is what the actual angular distribution of galaxies observed by the SDSS survey looks like. You can see there's all these stripes, there's these holes in the imaging, in the distribution. And this is because there's a bright star in front of all these galaxies, so you can't observe anything near there. These are from systematics in the imaging itself. So all of these effects have to be modeled accurately in order to measure unbiased measurements of the Lambda-CDM parameters. There's another issue that comes from the fact that right now I'm showing you an image of a focal plane of the telescope. So this is where the light reflected from the mirror goes to. And each of these holes that you see here is the positions of the galaxy, and where in the past we would manually plug these fiber optics cables to extract the light of the galaxy, which then feeds into the spectrograph. And so one of the limitations that we encounter is the fact that these fiber optics cables have finite sizes, which means if you observe two galaxies that are very close to each other, you can only observe one of them. So you have to just choose one. And so you're systematically missing galaxies, pairs of galaxies on small scales. And as you can imagine, these have significant effects on the clustering. So this is looking at the effect on the power spectrum as a function of scale. Gray is sort of the benchmark of, this is the statistical uncertainty of the measurements. And you can see these are with different simulations simulating the effect that this is a dominant effect, even on large scales. And we don't currently have any correction schemes for higher order statistics. And so this is a major challenge. So here's sort of the current challenge that we face if we try to extract all of the information in galaxy distributions with the current approach. But alternatively, instead of using the analytic models based on perturbative expansion of the density field, we can instead use simulations where, for instance, with the higher resolution M-body simulations, we can accurately model down to much smaller scales. And we can also analyze any statistics as long as we consistently measure it on the simulations as we do in the observations. And lastly, in terms of some of the observational effects, we have a lot of the tools to model all of the geometry of the survey, the effect of fiber collisions that I mentioned, and all of these things already built. So we can include it instead in the simulations rather than trying to correct for it in the measurement itself. And that's a much more effective way of accounting for all of these effects. So then the only challenge is, how do we go from a simulation of a galaxy survey to inferring the Lambda-CDM parameters, so the probability distribution of the Lambda-CDM parameters, getting this Bayesian posterior distribution over cosmological parameters. So the way that SimBIG does this is by using generative models. So what we do is we use generative models as a neural density estimation. So in this case, we have some flexible model Q with some hyperparameters phi, and our goal is to estimate this posterior, this probability distribution of Lambda-CDM parameters given the galaxy distribution using Q of phi. And so I'm sure many of you are familiar with this, but you can train Q of phi by minimizing the callback Liebler or KL divergence between P and Q. And for those of you who aren't familiar with this, you can think of this as some measurement of how different the two distributions are. And so you're trying to minimize this difference, which then gives you a very accurate estimate of what P is. So the advantage of this is that of the KL divergences, you can rewrite it strictly in terms of samples drawn from this joint distribution. So these are the simulations run at different values of the Lambda-CDM parameters, spanning the prior. And once you have this, you can actually estimate the posterior. So one of the models that I like to use in particular are normalizing flows, because they're very easy to evaluate and they're very flexible. So these are a series of invertible and differentiable transformations, and you can stack many of these in order to make it increasingly flexible. So without going into too much detail about this, I'll show you some examples of a 2D normalizing flow going from a Gaussian distribution to these two moons. Here's some examples in 3D where we're estimating the distribution of the planes, of chairs, or cars. So the question is, can we use a normalizing flow to estimate this probability distribution, training on cosmological simulations? And so that's the goal of the SimBIG framework, which stands for simulation-based inference of galaxies. And so the first step of this is to generate the training data of synthetic observations. So we start from different values of the cosmological parameters. For each one, we generate a synthetic galaxy survey that includes all of the details of the surveys, and that can accurately model down to small scales. We compress all of the galaxy survey data into some summary statistics. We use that then to train a normalizing flow. Then afterwards, once you have the trained normalizing flow, you perform the same data compression on actual observations from telescopes. You plug that into the trained normalizing flow, and that gives you the posterior of the Lambda-CDM parameters. So let me go into a little more detail about how we generate the synthetic galaxy surveys. So we start off again from the Quixote M-body simulations, which was the video that I showed you that traces the evolution of dark matter from the early universe all the way to the present. Then we again identify these dark matter halos, which are the virialized structures of dark matter where galaxies reside. Then afterwards, we populate these halos using a halo occupation distribution, which is a flexible way of putting galaxies into these halos that we've found is very, very successful at describing how galaxies are distributed. Then afterwards, we put all the survey realism. So we put it into redshift space. We apply all the geometry, the masking, the fiber collisions, all of the messy details of actual observations. And in total, we construct 20,000 of these simulations, where each simulation is from a different cosmological or galaxy parameters. So here's an example of what the synthetic galaxy survey looks like. So the left is the actual observations from Sloan, and on the right is one of our simulations. So you can see that here, all of the sort of details and imperfections of the observations are reproduced. And so they look nearly identical aside from the actual distribution of galaxies. The color here represents the. So once you have all of these simulations, you can then use this to train the normalizing flow, and then you can apply it to analyze different galaxy clustering statistics. So the first one we applied this to was the nonlinear.
So let me understand just what you've done so far. So the synthetic data came from your simulations, right?
Yes.
So you have enough to have a training set. So at this point, your normalizing flow is a way of turning the simulation into something you can sample from.
Yeah.
Like what's the difference between the normalizing flow model and the simulation model from which the synthetic data came from?
So the thing is, the simulations are expensive, so we can't run an indefinite number of these simulations. So the normalizing flow allows us to use, in this case, just 10,000 or simulations, and then sample over the different cosmological parameter space.
Okay, so let's see if I get this trick right. What you want to do, so the reality is you have a whole lot of data of cosmic surveys, and you want to compare the distribution of what the model's predictions are to the distribution of galaxy structures. The simulation is too expensive to just generate distributions at the scale you care about. I'm sorry, and once you have the distributions, you have the Taylor divergence metric to compare distributions to each other.
Yes.
You don't have enough compute time to run the simulation that many times, so you train neural surrogates so you can.
Yes.
Got it.
Yeah. So once you have, like you said, the neural surrogates, we can then analyze different clustering statistics. So the first one we analyzed was the galaxy power spectrum. But as I mentioned before, with the standard approach, you can only go down to K of 0.2, but because we're using these simulations where the clustering is much more accurately modeled, we can extend all the way down to 0.5. So here's what the posterior actually looks like. The top set of parameters are the Lambda-CDM parameters that we care about, and all of these are additional parameters that go into our simulation that we can also constrain, but we're not particularly interested in. So if we focus on the two parameters, omega matter and sigma 8, omega matter is how much matter is in the universe. Sigma 8 is how clumpy the universe is on large scales. The constraints we get from SimBIG is in blue, and the standard analyses using effective field theory is in orange from Misha Ivanov. So what you can see is that we're able to constrain sigma 8 significantly tighter than the standard analyses. So this is because we're leveraging that information on small scales, so on the nonlinear scales. So this is still just the power spectrum. So this is the 2-point clustering. So the next analysis that we did was on the galaxy pi spectrum. So the constraints that we get from SimBIG is in black here versus the constraints that we get from the standard analysis in orange. And you can see that by the size of the contours becoming much smaller, that we're able to improve the precision of our measurements on both of these parameters significantly. And this comes from the fact that we're now not only extracting nonlinear information, we're also extracting higher order information from the galaxy distribution. So another summary statistic we tried after the bispectrum was using a convolutional neural network to compress the entire galaxy field. And you can think of this as sort of an attempt to extract all of the relevant cosmological information in endpoint functions. And so when we do this, we find consistent results as the bispectrum analysis. And so we find significant improvements over the standard approach alone. So at this point, we've applied this to a number of different summary statistics that people in the community have been demonstrating is promising. And so all of that sort of consolidated is going back to the cosmological tensions before on S8 and H0, the Hubble parameter. Here's how the SimBIG constraints look in blue compared to the standard analysis in the black dashed line here. So you can see that we're able to improve this S8 parameter, which measures the growth of structure, about a factor of 2, and this H0, which is the expansion rate of the universe, by 50%. So one thing I want to emphasize here is that this improvement on S8, for instance, this factor of 2, this is equivalent to analyzing a survey of 4 times larger volume. So to put that into perspective, the total operating costs of BOSS was $15 million over 5 years. So this these constraints are equivalent to running a survey or the same survey for 20 years. So this, but of course, using this analysis costs much less than $60 million. So one of the exciting things is that right now, all of this analysis is done with existing observations, but the data from the next generation galaxy surveys will be really transformational. So this is a nice little figure showing you the number of galaxies that's been observed as a function of time. And I've plotted here the different sort of galaxy surveys of the past. And so you can see that these points sort of follow what we call the Moore's law of galaxy surveys. And so in the next coming decade, what this shows is that every decade we observe 10 times more galaxies. So in the coming decade, we'll also have two surveys, the dark energy spectroscopic instrument and the prime focus spectrograph, which will continue on this Moore's law of galaxy spectra and increase the number of objects, galaxies that we observe by another factor of 10. And so I'll talk a little bit about what these surveys are. So the Dark Energy Spectroscopic Instrument, or DESI, is currently observing in Kitt Peak National Observatory in Arizona. It uses a 4-meter Mayall telescope. This is the focal plane of the telescope. It's able to observe 5,000 spectra simultaneously, and it has these little robotic fiber positioners. So I showed you the focal plane before where people had to manually plug it into the holes drilled into aluminum plates. Now we have these robots that can position the fiber optics cable to the exact position of galaxies using these robots. And so using this technology, DESIs will observe over 40 million galaxies all the way out to redshift of 2, which corresponds to roughly when the universe was 3 billion years old, so 10 billion years of cosmic history. We also have the prime focus spectrograph, or PFS, which is observing in Mauna Kea in the Subaru telescope. So this is an 8.2 meter telescope, so significantly larger than DESI. And actually, the slide is incorrect. It's already started observing now. And it uses a similar technology with the robotic fiber positioners to observe 2,400 spectra simultaneously. And it'll observe galaxies, over 5 million emission line galaxies, all the way out to redshift 2.4. So this goes even farther and goes into, observes until the universe was only 1 billion years old. So we'll cover roughly 12 billion years of cosmic history with DESI and PFS combined. So to give you I've thrown a lot of numbers, but to give you sort of a tangible idea of what this data will look like, here's the distribution of galaxies from SDSS. So this is what the SimBIG analysis was currently conducted on. This is a thin slice through the galaxy distribution. And so compared to this, here's what we'll observe with DESI, and here's what we'll observe with PFS. So you can see that not only will we observe much, much larger cosmic volumes, but one of the really exciting aspects of this is that we'll have a much higher density of galaxies. So you can already see from this, this image that we'll resolve a lot more details in terms of the cosmic structure of the galaxies, which means there's much more cosmological information embedded in this distribution. So if we go back to this figure that I showed earlier in my talk, showing you the S8 and the Hubble tensions and the different measurements from different cosmological probes, what we'll get by applying SimBIG to DESI and PFS are measurements of both of these parameters all across cosmic history over this 12 billion years history. And more importantly, we'll be able to measure these two parameters with enough precision that we'll be able to either resolve or confirm the cosmological tensions that we find between all of these different experiments. And so really another way to think of this is that we'll make precise measurements that allow us to test the standard Lambda-CDM cosmological model, which means that we'll be able to probe dark energy all across cosmic history. So I'll end it here, and I'm happy to take any questions.
Well, yeah. Well, thank you very much. Well, first, let me clarify one big thing is differentiation between things like cosmic expansion, like the acceleration due to dark energy, from early inflation? How are these processes different, and like in terms of the fingerprints they leave onto the galaxies?
So you're referring to the expansion from dark energy versus inflation.
Right, like because you had several generations of like the universal history, and they all push different. They drive matter in different directions, and something like when it was like more dense, you had sound waves. That one I kind of very viscerally get, because sound waves, they look at very differently from gravity. But some of these other processes, it's unclear what fingerprints they leave.
So in terms of inflation and dark energy, the imprints are quite different. So inflation is the important process that is necessary to seed the initial perturbations in the universe. So if we had a completely homogeneous universe, we wouldn't have any structure. But with inflation, we have these small variations that eventually grow into the big differences between voids in galaxies versus highly dense structures. And so one of the features of this is, depending on different predictions of inflation, we predict different slopes on the inflationary power spectrum. So we're basically, the distribution of how clustered things are, the initial density fluctuations are, is a prediction that we can measure. But that feature is an overall sort of shape of matter clustering versus the dark energy, which is we actually use those sound waves as a ruler to see how the size of the universe at different time scales, and from that we're inferring the expansion of the universe. So pretty complementary, and not really, they're not degenerate in terms of the actual imprints that they leave.
Okay. And now you're pointing to some of the biases in the data set, like when it's hard to see adjacent galaxies, and like to what extent is the data set biased in difficult to untangle ways?
The short answer is yes. There's a lot of practical limitations of the current observations that we have. For example, one of the key measurements that we make is the redshift of a galaxy, or the velocity of a galaxy. Now, this redshift or velocity is something we measure from the spectra by comparing specific features in the spectrum and seeing what wavelength those features are detected. Mm-hmm. So we're using Doppler shifting to get the redshift. But different galaxies have different features. And so there's certain regimes where it's not like you can really follow a single type of galaxy all throughout cosmic history, because at some point that feature will no longer be visible by our instruments. So you then have to follow a different galaxy population for certain epochs of cosmic history. So our sample of the galaxy distribution ends up being sort of a hodgepodge of different galaxy populations stitched together. And so modeling all of that is one of the main challenges that we face.
Okay, so, and what details do you model? Because you have your galaxy simulator. So what needs to be captured in that thing for sufficient fidelity?
So depending on the galaxy population, the way they reside inside of a dark matter halo, so inside these large dark matter structures, is quite different. So massive red galaxies, these reside near the center of the halo, so they're relatively easy to model. Mm-hmm. But the bluer galaxies, which are the ones we need to model for higher redshift, so earlier on in the universe, they no longer reside near the center. They're more likely to reside at the outskirts of these halos. So mm-hmm. Then in detail, if we wanted to really model them, we have to model the detailed gas physics and the baryonic physics, because this is a matter of gas infalling into the halos, cooling to form these galaxies and to form the stars. And these are physical processes that span many, many orders of magnitude. So you would simultaneously have to resolve the extremely large scales, cosmological scales, as well as the scales of stars and gas. So for instance, there currently really isn't a simulation that we can do that models all of the physics along all of these scales, simply due to the computational limit of it. I think a similar analogy is a lot of our climate models, because I think they face similar issues where you have the large scale sort of modeling challenges, and so you can't resolve all the different physics of all the scales.
Okay, so it makes sense. And then borrowing from them, to what extent? So you took a particular simulation with a particular set of choices of what to resolve, and then and that was already too expensive, so you neurally surrogated that.
Yeah.
Now another way of using neural surrogates is to take. I get the impression that your simulator doesn't do galaxy structure, but if you had a neural surrogate of that thing, maybe you can plug it in, and this more compositional approach to simulation design. Would that make sense?
Yeah, so that's actually one of the approaches that we're taking now. So we're some of the more detailed, what we call subgrid physics of galaxy formation. We can learn those from much higher hydrodynamical simulations of galaxies, and then sort of use that to paste the physics onto these larger simulations. But one of the challenges there is that even the higher fidelity hydrodynamical simulations, many of the physics, like if you take all the different models at the moment, they have a large variance in their prediction. So if you looked at the same galaxy population in multiple different hydrodynamical simulations, they would behave quite differently. So the theory hasn't really converged on these galaxies. So you need to do the neural surrogates in a way that allows you to marginalize over our current ignorance of the galaxy physics. And so that poses an additional sort of challenge for us.
And how does dark matter? What is your model of dark matter? Like, is it like it doesn't interact with itself but has mass?
Yeah, it's a collisionless gravitational model.
Okay, so then a lot of the hydrodynamics don't matter, given that.
So for the dark matter, it doesn't. But because dark matter constitutes 85% of the matter, it's kind of the skeleton running behind, like in the background. So all of the baryonic physics has to operate with the dark matter evidence. But dark matter alone is much cheaper to model.
Right, and I get the impression that it's more like cosmic filament granularity structures are, you have to resolve dark matter forms. Is that right?
Yes, yes.
Okay, so then, that's one model of dark matter. It seems like your scale is about right for evaluating different models of dark matter, or even modified physics, the modified gravity, because it's also at about that scale.
Yes. So yeah, we can use the same approach to test different theories of dark matter. So there are common models now currently are dark matter that interacts with matter at some energy regime, and that would have some inference. But at the moment, based on constraints from direct detection experiments of dark matter, the energy levels are so low that the features would not show up yet in the galaxy distribution.
I mean, it would take a much older universe for us to see it.
No, I think or we just need to have a much higher detailed image of the galaxies in order to actually notice such a subtle effect. Because otherwise we would have detected it in other experiments of dark matter where they actually test for direct interactions between dark matter and some giant vat of dense liquid. Got
it. So then, to what extent can you start upper bounding the how strong of an effect it can possibly be to have so little, I'm talking about pretty much any dynamics, hydrodynamics for galaxies, effects of dark matter, and baryonic interactions. Can you start upper bounding the size of these effects?
So currently, with the existing observations, there are upper bounds, but they're not actually interesting yet. But with the new generation of surveys that I've talked about with DESI and PFS, we'll finally get to that regime where we'll get competitive upper bounds.
Okay, it makes sense. And so one thread that you started pulling on was you're having generative models of galaxy structure, and that I got the impression that basically your simulation is a generative model, just a very slow one.
Yeah.
and you're training one family of models, but now the number of random generative models have exploded. To what extent is that useful? It sounds like it's a 3D transformer kind of thing will be relevant for this.
So that's definitely a sort of, now people are looking into this more. There hasn't been, I think one of the challenges all of these investigations have faced is that at the end of the day, compared to, I guess, in industry, the amount of training data that we have, so the simulations that we have, are highly limited.
Yeah.
So it hasn't been extremely effective, or it's been a real challenge at training some of these generative models very accurately. And at the same time, the fidelity that we need for the generative models are very high. So there hasn't been like a good sweet spot where they've been useful so far. But it's definitely something that the community is exploring very actively.
Okay, makes a lot of sense. Well, I think, yeah, that I think covers all the directions. Yeah, thank you very much for your time.
No, of course. This was a lot of fun.
Yeah, thank you. Have a great rest of your day and safe travels.